Controle. Es muy pequeño, ahí se ve grande.
The numbers are this, I can, so I can enlarge. Thank you.
Maybe you can try to read it there. It's hard for you. You need to
Look there. This is the place where I wonder if I would have.
For the next page,
Now I can do that.
¿Ya empezamos? Sí.
Bueno, la matemática, para los que no somos, o sobre todo los que somos bien, es un mundo misterioso y fascinante. Así que,
Muy bien, estamos aquí reunidos con motivo de la incorporación del doctor Reunión, matemático de los Países Bajos, Netherlands, a la Academia Nacional de Ciencias. Rudolf Reunión nació en Speel en 1944, es una ciudad pequeña de 130.000 habitantes, a 50 kilómetros al noreste de Utrecht. Realizó estudios universitarios de grado en la Universidad de Utrecht y luego de posgrado con una tesis doctoral en el año 1972. Hizo una estadía postdoctoral en la Universidad de Yale en 1972-73 bajo la supervisión de Sir Lang. Desde 1978 es profesor de la Universidad de Utrecht. Ya está jubilado, pero continúa sumamente activo en sus investigaciones. En 1978 publicó en en la revista Invenciones Matemáticas un trabajo muy relevante simultáneamente con un matemático ruso, Alexander Kuznetsov, que es la llamada fórmula de la suma de Brueggemann-Kuznetsov. Esta es una fórmula análoga a la fórmula de la traza de Selberg para un subgrupo discreto de SL2R de covolumen finito. Resuelve el problema de calcular la traza de un operador que podemos llamar PDF en L2 de G sobre el subgrupo discreto en dos maneras diferentes. Esta fórmula relaciona coeficiente Fourier de formas automorfas con sumas de Klosterman y ha tenido numerosas aplicaciones y generalizaciones, algunas de ellas en colaboración conmigo. Rudolf es un matemático a la vez profundo y muy fuerte técnicamente. Trabaja en teoría analítica de números, pero conoce bien análisis armónico, geometría algebraica y topología algebraica. Ha publicado trabajos importantes y extensos en excelentes journals. Invenciones Matemáticas, Mathematician Allen, Duke Mathematical Journal, GAFA, Journal für die reine angewandte Mathematik, tiene 3 trabajos ahí. En el Journal of Number Theory, tiene 2 trabajos. En el Memoirs de la American Mathematical Society, 3 trabajos que son prácticamente pequeños libros. Lecture Notes in Mathematics, IMRN, Transactions of the American Mathematical Society, Mathematische Zeitschrift, Asian Mathematical Journal of Mathematics, and Algebra and Number Theory, y otras revistas. Ha realizado colaboraciones con matemáticos muy reconocidos como Don Zagier, del Collège de France, París, John Lewis, USA, Motohashi, de la Universidad de Tokio, Fritz Grunwald, de Düsseldorf, Dieter Mayer, de Klaus Hall, Anke Paul, de Bremen, Young-Yu Choi, de Corea. Colabora con la Universidad Nacional de Córdoba, indirectamente, desde 1993. Tenemos varios trabajos conjuntos y asesoró las tesis de varios estudiantes de posgrado, Leticia Barcini, Inés Pacharoni, Patricia Kiwi, Ángel Villanueva, Cintia Will, Emilio Laurel. El inicio de la relación fue un viaje al International Center of Theoretical Physics mío en 1993. En realidad, ya en 1989 la cosa estaba muy dura y había pocos recursos en la Argentina. Yo me presenté al Centro de Física Teórica de Trieste, y me nombraron associate, y con eso pude hacer 3 viajes. Y bueno, Trieste es hermoso y era muy agradable y un excelente lugar de trabajo, pero había poca gente, y bueno, en el último viaje de esos, yo decidí que quería aprovechar para ir a Europa un poco, entonces me subí a un tren y empecé a trasladarme, fui a la Universidad de Nancy. Entonces fui dando algunos seminarios y hablando con gente, y el tercer seminario yo quería darlo, conocerlo a Rudolf. Y bueno, él me esperó en la estación de tren, y ahí inmediatamente me dijo que esperaba que eso fuera el comienzo de una very fruitful relation. La cosa que, bueno, yo decía, bueno. Entonces fui, estuve 4 días ahí en Utrecht, en la universidad, y bueno, y trabajamos, y yo tenía algunas ideas de generalización del trabajo de él, y entonces yo manifesté mis ideas. Bueno, él inmediatamente se subió, y bueno, la cosa es que cuando yo volví a la Argentina, digamos 10 días después, ya tenía en el correo 10 páginas tipeadas de lo que habíamos hecho. Y bueno, y después me tocaba a mí hacer la otra parte, ¿no? Bueno, por supuesto que yo demoré un mesecito, digamos, para porque había estado un mes afuera, bueno, tenía muchas cosas que ocuparme. Pero bueno, ese fue el comienzo de la colaboración y el trabajo salió en el Pew Mathematical Journal en 1995. Bueno, ese fue un comienzo de una serie de trabajos que pudimos hacer. Él fue un gran colaborador en las tesis de Leticia Barcini, Inés, y con Inés hicimos algunos trabajos conjuntos. Inés visitó Utrecht 2 o 3 veces, y bueno, y la relación ha seguido, porque yo he seguido viajando y Rulo ya vino 5 veces acá, conoce Tampi, Mar Chiquita, la esposa es botánica, entonces ha estado muy interesado. Bueno, el Rulo es, además de un excelente matemático, una excelente persona, muy generoso, muy humano y muy agradable para trabajar con él y para conversar de muchos temas. O sea, es una persona que no puede hablar de historia, de las guerras, de las monarquías. Bueno, yo recuerdo que Tito Grumbaum solía decir, cuando se refería a algunos de los personajes del PAMA, decía: el problema que tiene porque cuando uno lo criticaba, Grumbaum encontraba la forma de decir, no, pero el problema que tiene él es que no lee los diarios. No lee los diarios, claro, y una persona que no lee los diarios, entonces tiene ideas un poco general. Bueno, no lee nunca los diarios. Bueno, la cosa es que Rudolf sí los lee con mucho cuidado y sabe, digamos, lo que sucede en el mundo, no fútbol, pero tiene un gran sentido del humor, aunque no cuenta chistes como los cordobeses contamos. Bueno, a continuación le daremos los atributos que lo acreditan como académico de la Academia Nacional. Bueno, ahora Rulo va a dar la conferencia de incorporación.
First one page. Yeah. Me alegra de estar aquí en esta respetable academia y quiero agradecer por la Incorporación. And thank you, Roberto, for the words, but I want to read what you exactly said. In this lecture, I would like to tell you a bit about a subject that is a large subject. Many famous mathematicians have you have contributed, and I have been involved only in a little tiny bit of it. So I am aware that this is a complicated mathematical subject, and I try to give you an idea by just explaining two examples. So I first oh no, yeah, it is. The first example is the torus, what in the US context is called a donut, but it's not the three-dimensional picture that is at the center of my attention, but I cut it open. When you cut it open, you get a rectangle, and I deform it into a square. And you can identify the torus with the square when you glue this upper line and this line together, and you glue this left line and this right line together. Of course, when you try to do this with paper, one gluing goes right, so you get a cylinder, but paper, you cannot stretch it, so you don't get this nice picture. You have to have elastic material to do it. But mathematically, I look here, and I'm interested in lines on this torus, and you see this green line, this top line, and this bottom line are the same line here, and they form a circle on the torus. Oh, it's visible, and the left line and the right line are the same by the gluing, and they correspond to another circle on the torus. But I speak about lines because I look at the geometry of this rectangle, of the square, and with this identification. Now, we put lines on the torus. Here it might be good to try to make it larger. That is too large. Yeah. When you start here at the bottom, this you go in a fixed direction, then you arrive at the right line, but there's this point 1 is the same as this point 1. Oh. And then you go on, and this point 2 is the same as the bottom point 2, and you go to point 3, that's here, and you go on here, and then you end on the top right corner, and because glues the top and the bottom line, and the right and the left line, this point is the same as this point. So this line comes back to the point where it started with the same direction. And so if you just look at the torus, then it is just a line with finite lengths on the torus. In the other picture, I gave a slightly different direction. We start here, you come here at point 1, but this point is also this point, and then you come here, but that's also this point, and so you go on and go on and go on, and finally, then you give up. You can, and then you don't know whether you come to the same point again or not. So for this line, it is not clear whether it is a closed line or not. There is another way to That's the thing. Now I try to make it smaller again. It's on the screen. So we have we have a closed line and a free open. Now, I thought this is the picture of the strain I want. Instead of looking at one square, you look at the next square, the square here. You can look. We have to identify this line is this line. So here you are back at this point. So and this, sorry. If you are here, then you have this is the same torus. This square represents the same torus as is represented by this square, and you can tessellate the plane by squares. And each square represents the same torus. That seems a bit superfluous that you take an infinite number of squares, but the advantage is that then you can you can see what the closed line is. That the closed line that we saw here in the in one of the previous screens, if you put it into this tessellation, then the line looks like a line. Of course, you know that this point is the same as this point, but if you have this representing square, then you can just go on. So the four pieces of the line that we have, if we look only at one square, will become just one line. And then we could also start at this point, and then we get the same line on the torus again. And the point is that you here come back to the same point here. This was a corner point, and this is a corner point. So in this way, you have the closed line because it comes when it goes from a corner point to a corner point. The other line, where is it? The other, here it is. If you do it there, then you see that at a certain point we stop because we don't want to go on infinitely often. So also the tessellation does not show us whether the line is closed or not. But what does it mean that it comes ultimately to a corner point again? That means that we go a certain number of steps to the right and a certain number of steps to the right, and the quotient of those two numbers is the slope of the line. And here in the first I had a slope of 2/3, and here I know that I computed the slope 1/√2, and you cannot write that as the quotient of two integral numbers. So I know that this line is not closed. What would you see here if you really go on? Yeah, you would see a black square because the line comes everywhere near any point without any, so it fills it up. It would, and yeah, if you draw it, you need that a line with a certain thickness, so it really becomes a black square. So in this part of the tessellation, let's see. I want to be a little bit. Well, how do I go to a little bit ahead about it? Oh. Yeah, now it is larger and that, and it doesn't fit. Sure, it doesn't fit. Now let's see. So now we have the closed line. Thank you. The closed lines. This is what I said. If a line is closed, it comes back to a lattice point, and then at a lattice point you can give it coordinates. If this point you start with, you may give the coordinates 0, 0, and then you come to a point with n steps to the right and m steps up, and that with integral numbers. So this is, and we could go to the line with a negative slope, then we would go in another direction. But anyhow, for any two choices of integers n and m, for any choice of two integers n and m, we get a closed line. And any other slope does not hit a corner point again and is not closed. So you have the closed lines on the torus are very special, and you can see how many there are. Now, I made a little table. Length 0 is just starting at a point and stopping there. Corresponds to n and m equal to 0, and that occurs only once. If we have a square of length 1, then either 1 is plus or minus 1, or the other is plus or minus 1. And so we have 1, 0, minus 1, 0, and 0, 1, and 0, minus 1. And that gives 4 possibilities. And so you can go on lines of length square root of 2, that then you go straight by a diagonal of the square, and that can also be done on 4 ways. And now at a certain moment you get possibilities 2 steps to the right and 1 ahead, and that can be done on 8 ways. So you get a set of numbers, lengths of the closed lines, and that is not a set of numbers, but you have a list of numbers, and each number can occur a finite number of times. And that one calls the length space. That is the length spectrum of the torus. Then you can also consider the wave equation of the torus. Then I want it a little bit up so that the last line is visible. Thank you. That is better. Thank you very much. I'm glad to have so many help. When you have this torus, you can consider it if you have a real torus and you might make it of some metal or so, then it may, if you hit it with something, then it may give a tone, and that is not the tone that you get when you hit the square, but when you take, because the torus, as we saw it, were deformed. It was a deformation of the square. The distances cannot be the same on the torus and the corresponding points on the square. And we look at the geometry of the square, and then you may have, for instance, some physical field that gives an oscillation. And for the simple equation to describe all this type of oscillations is the wave equation. That is a bit more complicated. There you have a partial differential equation that not all of you might be familiar with, but you see there is a quantity u that indicates the oscillation. There are the coordinates x and y on the square, and they run from 0 to 1. And you have the time, and the partial differential equation says that what relation you should have for such a simple oscillation. And this differential equation can be solved, and you can build all solutions from simple solutions. And there I take the freedom to use complex numbers, because then you get an easy way to describe the solutions. You can write it in a real way and then describe it with cosines and sines, but this is much nicer once you are used to complex numbers. And you see in this equation, you have an exponential where nx, ma, and multiple omega t of the time t occur. The parameters n and m should be integral numbers, because if you do enlarge x or y by 1, then you should be on the same point on the torus of the square, and so n and m should be integral numbers. This omega should is not a reason that it should be integral, but what turns out is, if you look at analyze the differential equation, is that this omega depends on n and m. And the formula is given here. It is some multiple of the square root of n squared of n and m, the squares of n and m. And that is the same number formula that we have seen for the length of the closed lines. Lengths, they are all have also lengths given by the square root of n squared plus m squared. And here you get a multiple of the same length, of the same number, and you see that the frequencies omega of the oscillation are a fixed multiple of the lengths that occur in the length spectrum. So for the torus, you see a very interesting point, that the length spectrum and the frequency spectrum are closely related. You have a set of numbers that can occur a number of times, and if you have one set and the other set, it is just multiply the elements of one set, but of the length spectrum by a fixed number, and then you get the frequency spectrum. And of course, it goes the other way around. So this is a simple example where you see that the length spectrum and the frequency spectrum of this surface are closely related. If you want to do this for other surfaces, you have to think about what is needed. You will have to know what is a straight line, and the technical term for a straight line is a geodesic. You have to be able to speak about lengths of line segments, and you have to have some generalization of the wave equation. Now, these concepts of lengths and the wave equation, the differential equation, they are provided by a Riemannian structure on this space, and that's just a name at this point. Now, I look at one more example we have that's the hyperbolic plane. That is a very nice example. I should be here, I think. That is a nice example of a strange geometry. It consists of all points above a line that we may think as the points with the xy plane with y positive. And you decree that the lines in this hyperbolic plane are just the circles with their center, the half circles with the center on the axis, and the vertical lines that you might also see as a circle with the center at infinity. But just if we look at it is a nice geometrical construction, and you see that yeah, if you have 2 points in the upper half in this half of the plane, then you can always find exactly one of those strange lines that goes through those 2 points. But if you have a line in normal geometry, we are used that there is one line that doesn't intersect it, that's parallel. But here you can have many parallels. So this is a model of the hyperbolic geometry that departs from the Euclidean geometry that we are used to. So now we take this plane, this hyperbolic plane, as to form the next example. Here we have all lines have infinite lengths, and the lengths of any curve, those lines and all of those circles and lines, are given by some formula with an integral. And if you omit this y in the denominator, you get the lengths that curves. You get an integral that describes the length of standard for the standard geometry, for the standard Euclidean geometry. But you divide by this y, so little pieces that look the same, low down and high up in the plane, in this half plane, they have a very different length. If you are high up, then y is large, and so the length is smaller. And if you let y go down to 0, then the function that you integrate, it grows. So if you are near this line, this horizontal axis, then a small piece in the standard geometry has already a large length in the hyperbolic geometry. Also, for the wave equation, you have a fairly straightforward generalization. It's written here in a slightly different form, and the appearance of those factors y square and y square are coupled to with the y here in the denominator, and so that means that this is the right way to write the wave equation when you have this geometry. Now, then all those lines in the hyperbolic plane, those vertical lines and the half circles, have infinite lengths for this formula. Now, what we do now is similar to taking this square in the for the torus, to build the torus. You say, oh, I take a vertical line, so that's the line, a hyperbolic line at the point based at the point -1/2, and you take another one, a vertical line, at the point 1/2. And here you take the hyperbolic line that is given by a circle with radius 1 and a center at 0. Then you get a triangular region here, and you start gluing. You glue this vertical line to this vertical line, and this vertical line to this vertical line. To do that technically, you have to make sure that this gluing respects the distance, the length, the concept of length that you have formed. So, there's work to be done. And the formulas given that give these gluing relations can be easily written in complex notation, and just z goes to z plus 1 corresponds to a step of length 1 to the right, and z goes to minus 1 over z is a more complicated transformation, but it has the property that this green piece is moved to this green piece. So the point here is fixed, and this is at the same point, at the same points of the boundary. And if you glue in this way, you get something, that looks a little bit like a ball, but it has this way to go to infinity, and that is an infinite ball from which an infinite tentacle arises, and it's infinite, but the tentacle won't become smaller and smaller, because the distance concept, distance that looks in the Euclidean picture the same, gets less and less when you go up in the hyperbolic plane. So this is this surface that you are that you arrive at by gluing is called the modular curve. People would say, "Oh, why do you call it a curve? It is a surface." But this is called the modular curve because people who study it often work with complex numbers, and then you have one coordinate. And I do not want to call it a modular surface because that means something different. All right, so here we have another analogous space surface correspond that plays the same role as the square in the first example. We can tessellate the plane, and you see here this one triangle, and it can be shifted a number of steps to the right. It can be transformed. This can be transformed into this region and to this region, and of course you can. There are infinitely many circles here that you cannot draw, because this line is more or less infinity in the hyperbolic geometry. Anyhow, we have here the way to a tessellation. Now, what are the closed lines? Then there are lines, parts of a hyperbolic line that go from one point to another point that corresponds to the same point on the modular curve. And here I take as example the line that goes through the top of this arc and to the top of this arc. And if you describe it with complex numbers, then you go from I minus 1 to I plus 2. But this is a hyperbolic line, and because in the tessellation you see it that it is a line, so that this direction here corresponds to this direction here, and you have a line that comes back to an equivalent point with the same direction. That's a closed geodesic. Like in the case of the square, you can pull this back to one of those triangles, then you get this piece corresponds to this line. Then you go on with this piece that corresponds to this line, and yeah, this point and this point are the same, so that goes on. This point is the same as that point, so you go on and you have this part, and you go back via this line. So it's this is the most simple example that you can find, but there are many of them. There is the closed geodesics, the closed lines on the modular curve. They are known and you can enumerate them, and I have here given the technical formulation how you do it. But there is a concept of line and you get a length spectrum. Now then the wave equation has also known solutions, and it turns out that it's sensible to look at solutions that go to zero if you go up on this infinite tentacle. And then you have the wave equation, and you find solutions of the form a function psi of the place coordinates times a factor that gives the oscillation. Those functions, psi of j, are the so-called mass waveforms that Maas introduced because there are a number of theoretical reasons to look at these functions. And there's a large difference between this example and the first example. None of these, you know that there are infinitely many mass forms, but none of them is explicitly known that you can write down a formula for it. You can, with finite element methods, with a computer, find numerical descriptions of the mass forms, and there it can be said a lot of it, but explicitly there's no explicit formula for it. Now then you can ask, is there here a relation between this length spectrum and the frequency spectrum? And the answer is yes. There is the famous trace formula of Zelberg, who gave a complicated formula in which you can relate the frequency spectrum and the length spectrum. And that is you can do a lot with it, but there is a way of using a technique of transfer operators that gives a way to describe the frequencies that you get as the frequencies of those mass forms. That is the name Meyer is the first one who did it, and this is the part where I have done a little bit where you use this transfer operator to look at mass forms and generalizations of them. I say a few more words about the trace formula. It's a complicated formula, but you see in it one term where you sum over all lengths in the length spectrum, and you take the value of some function on these lengths, and you sum that. You take this infinite sum and you show that it converges, and you have the same for the frequency spectrum, and you have functions f and g. Of course, you cannot pick f and g arbitrarily. You have to have conditions to have convergence and to be able to relate this sum and this sum. Those functions f and g, one of them can be chosen rather arbitrarily under some reasonable conditions. And then the other one is determined by an quite involved integral transformation, but it's almost the essential part of this integral transformation is just to use your Fourier transform. That is quite well known. And that makes that you cannot, there is a certain uncertainty principle. If you take this F so that it sees only a little bit of the length spectrum, then this G is not a straight that sees, you need a lot of frequencies to get the, to determine this term. Or you could say, oh, I take G such that I see whether there are frequencies in a small region, but then you have to sum over essentially all length values. So it is a very nice tool that has been used a lot, but there's more to be done, and that transfer operator approach is one of the ways to do that. To do that more explicitly. Anyhow, this is the second example. You see, it's much more complicated. You don't know the length spectrum. You know the length spectrum, I say, and you don't know the frequency spectrum, but you relay them, and then can get information about densities, or how fast those frequencies grow if you let their number increase. So there is quite some relation, but it is not as easy as for the two others. Now, I hope with these two examples to have given you an impression of a fascinating part of mathematics, and gracias por su atención.
So why do you say that the length spectrum it's determined in this case?
In the case of quantum mechanics, you have to go from one point to another point. They're given by the group of translations for the hyperbolic metric, and it should be a translation. It should be in hyperbolic elements of the group that's describing the symmetries. And the technical term is the primitive hyperbolic elements in the modular group, and they can be the conjugation classes and they can be computed. It's work, but it is at least explicitly known. You can let the computer run and give explicit expressions for the first few hundred. If you change the group, it's the same formulation.
The same way.
It's the same formulation that if I think all co-finite discrete subgroup of PSO2. PSO2R. Then it works. Then the group is much less known, and then it will be hard to describe the length spectrum as well. But the trace formula of cellback goes through.
Bueno, si no hay más preguntas, entonces y lo que está presente, vamos a un pequeño video aquí al lado. Así que buenas noches.